Today we are going to talk about efficiency of solutions, in particular of Nash equilibria, and we are going to look at several important applications, some of which, well, not exactly what we are looking at, but they border in a way applications which were recently studied, and similar applications, more complicated but similar, are being studied right now. So that's in a way a gateway from which you can, if you continue, reach the front line of modern science. So we are going to study efficiency and its applications. And now let us begin with some examples, which we have already seen, in the following sense. So some games have only inefficient Nash equilibria. For example, we know this example prisoner's dilemma. Let us look at this in a general sense, so that you have cooperate C and defect D, and Z is smaller than 1, so we don't care which values there are here, as long as the value that you get when you cooperate and the one player defect, you get the so-called Sakos pair. So you get the worst pair. Now, if both defect, it's not good, but it's better than getting the Sakos player. Nobody wants to be the Sakos. And that is written in the formula that y is strictly larger than z. Of course, if they could both cooperate, then they would get x, which would be strictly larger than y. And if you manage to defect when the other person cooperates, or you manage to screw the other person, colloquially speaking, then you get w, which is even larger than x. So basically, these inequalities, they basically encode all those conditions we discussed. Now, however, we write another assumption, which is not necessary for our goal, but we will need that simply to be sure that the total utility is maximized when both cooperate. So that if both cooperate, they both get x, so 2x is strictly larger than z plus w, the total utility when one cooperates and the other one defects. It's clearly larger than 1 plus y because y is strictly smaller than z. Actually, we can assume that it's at least as large, not necessarily even that it's strictly larger, because we are going to need just to know which formula, which expression to use for the largest efficiency. So there is no need to say that it's always strictly larger, or we could have also managed with z plus w being strictly larger than 2x, simply then we would use that z plus w as the largest social welfare. We just need something. So let us write that at least here we don't necessarily need that it will be strictly smaller. And here the Nash equilibria, as we know, it's only when both defect. It's also a strictly dominant strategy profile, so that's stronger than Nash equilibrium. And if you look at the efficiency that we get here relatively to the maximum possible efficiency, then, well, let us look in, I'll reformulate. Let us look at the maximum possible efficiency in this game, which is, according to our assumption, achieved when both play cooperate, 2x. And as I said, we could have also assumed that it's achieved when when one plays cooperate and another one plays defect. Simply we needed to assume something. And anyway, according to the assumption that z plus w is at most 2x, the largest possible efficiency is 2x. Regardless equilibria, that's simply the largest possible efficiency in this game. Now, the worst case, however, that we can have in a Nash equilibrium, what is the worst we can have because we play a Nash equilibrium? Well, since we have only one Nash equilibrium, that's simply what we have when we play this equilibrium, so when both defect, it's yy. and the ratio is X over Y. So the price of anarchy, I remind that's the worst that we may have to lose in a way to pay. That's the reason for this word price. The worst we may have to pay because there is anarchy, because players play according to what they want and not according to some script from above. So this price of anarchy is X over Y. Now, what is the best that we need to pay? So what is the best we could have, the least bad thing, what is the least price we might pay for playing equilibrium? In other words, what is the maximum social welfare over the maximum possible social welfare in a Nash equilibrium? It's the same because there is only one equilibrium. So it's also X over Y. And therefore we conclude that price of anarchy is here equal to the price of stability, which is always the case when you have a single equilibrium, and that's X over Y. Since X and Y can be chosen as we want, that's basically something which implies that we can have very bad, we may have to pay a very high price for having to play an equilibrium. And if you assume players play an equilibrium, here it's even strictly dominant strategy. So this is an example when the fact that players, we assume, pursue their own good makes them as a society really, really bad off, and this even cannot be bounded reasonably. Now let us look at an opposite example, the simple coordination game. So there are two Nash equilibria, X top left and bottom right. So this one and this one. And that's also the optimum possible thing, the optimum possible total social welfare. So the ratio of the best social welfare in any profile to the worst social welfare in an equilibrium is 1. And also that's the ratio of the best social welfare to the best Nash equilibrium, because the worst and the best Nash equilibrium have the same. There is only one. No, there are two equilibria, but they both have the same impurities. So here, any equilibrium is socially optimal. So here actually we have a very nice bound that we don't have to care as long as we assume that players find and stay in equilibrium, that will be socially optimal. Another example, which is kind of in between those examples we have seen before. So one was really bad, the other one was really good. Here we can have both. So we have two equilibria here, top left and bottom right. By the way, I will sometimes expose the content of the slide gradually, so that if you want to think before I say something, you are welcome to stop the video, think, and then compare what you've thought with what I say. So there are two equilibria, top left and bottom right. When I talk about equilibria, I'm speaking about pure equilibria. If I want to say something about mixed Nash equilibria, then as a result it will be mixed price of anarchy or price of stability. I will concretely say this. So unless stated otherwise, I'm speaking only about pure equilibria. And the price of anarchy here is the ratio of the best possible utility here, which is 1, 1, to the worst possible equilibrium, which is 0, 0, which is infinite. So there is, in the worst case, an infinitely large gap, an infinitely large ratio between the best possible profile. Doesn't matter that it's also an equilibrium, but it's a best possible profile and a worst possible equilibrium. And the most optimistic situation is the ratio between the best possible profile and the best possible equilibrium, and that's the same. So it's 1 plus 1 over 1 plus 1, so it's 1. So we have both an optimal equilibrium, an optimum equilibrium, and an infinitely bad equilibrium. So here, the question is which we are going to play. So let us just make quick, simple conclusions from the three examples we've looked at. In the prisoner's dilemma, there is only a bad equilibrium. Well, it can be bad if we set the parameters badly enough. So no regulation will help if we assume players will play in equilibrium, and that's very reasonable because it's not only an equilibrium, it's not only Nash equilibrium, it's also a dominant strategy, a strictly dominant strategy profile. So we really need to change the interaction somehow to allow them to just to change the game so that they will be able to commit somehow to some behavior which will eventually benefit both, but any regulation will not help. Now, in the other example, we had only, I remind you, only optimum equilibria, so there is no need in regulations. No regulation is needed as long as we assume that some equilibrium will be found and played. And in the last example, actually it's a prominent example that we do need some regulation. So at least some hint, at least some directions about what can be done, some guidance can be used, because there is a good, an optimum actually, and an infinitely bad equilibrium. So it's important to know what are those prices of anarchy and stability, and that's the topic of today's lesson. So the plan is, first of all, to talk about the need for those measures, and we have basically covered that, so that we can sometimes say what we can guarantee, that's the price of anarchy, but we also can say what can be achieved if we pick the equilibrium ourselves, if we kind of can enforce or at least recommend an equilibrium for the player. That's the price of stability. And if we cannot guarantee much, but we can have a nice equilibrium which we can recommend, then there is some need in regulation. If we can guarantee something, then there is no need in regulation. That's really good, because sometimes regulation can be really, really expensive, or simply we don't want to enforce people, especially if it's not needed. And if we cannot find any equilibrium which is good, I mean, even if there exists no equilibrium which is good, so even if the price of anarchy is high, then we need to think about how maybe to change the interactions, how we can maybe adjust the interaction so that we will have at least some reasonable equilibrium. So we need those measures, and then we are going to use price of anarchy stability, and those measures, we are going to define them again. We looked at them once, we are going to define them again, and so that we have exactly a fresh memory of what they are. And then we are going to look at some very practical and theoretically important examples. Theoretically important because the techniques used there are often used, and we are going to have a very, very brief taste of those. So there are many courses, and there are many interesting papers and books which deal with those. So the examples I'm going to give are mostly from the book Algorithmic Game Theory. That's from its third part. And there are, as I said, many, many other sources on the topic, and some more complicated, admittedly, games are being studied right now. So you are definitely welcome to study and eventually to work in those areas. So this is the first example, network routing. That, as you can guess, is a very practical example. Then network design, when you build the network. So network routing is about finding a way in a network. Network design is about connecting, scheduling. Speaks for itself. Resource allocation is also a very practical topic, so that's definitely something we need in computer science. Then we're going to discuss efficiency as a standard, as a kind of as a yardstick for mechanic design. So for a reminder that mechanic design is basically indenting a game such that if players play according to the model we assume, so that if they have the utilities we assume, the strategies we assume, and if they play according to the solution concept, for example, Nash equilibria or whatever, then they play in some way like we want them to. And mechanic design, that's the area which designs games such that players will play whatever we want them. In a way, it's dual to analyzing existing games and saying what the players will do. So one of the measures, one of the characteristics we need to attain when designing such a game is that the game will have a good price of a lower price of anarchy, at least a lower price of stability, so that preferably the game will always be good for the society in an equilibrium, but at least there will be some equilibrium where the game is good for the society, and that can be used as a measure for how good the mechanism, the design mechanism, or in other words, the games, the rules of the game, how good they are. And then we're going to look at other examples, at atomic routing games. So first we're going to look at network routing, which is non-atomic, and then atomic. Now the difference is that if you look at atomic routing, then it's a game which falls under the model we've been discussing. So it's a game which has a finite set of players. Each player has some strategies, and given a strategy profile, each player obtains some utility. Now, simply the strategies are the routes, and the utility is usually what do you get from the route, how much flow of goods, for example, you manage to maintain, to run through the network. But there is another version of this game, and that's non-atomic routing, which is the network routing first example. Here we assume that there are infinitely many players, each responsible for an infinitesimally small part of the flow. Now, formally, we don't look at single players, we simply look at flow, and we define what is an equilibrium of the flow. We probably won't define it formally on this lecture, but that's the intuition behind the formal definition. So there are infinitely many players. Each player controls an infinitesimally small number of amount of flow, and we look for a stable state. That's when no part of the flow, no continuous part of the flow needs to move, can move and improve what there is. So that's not a game under the model we have been looking at till now. So this requires another definition of equilibria, which are inspired by this intuition I just said. And we will look at this not completely formally, but to a certain level. But this can be formalized actually quite easily. And as I said, atomic routing is a concrete case of a game, because simply here a player has an atomic, so a non-divisible, the players are not divisible, so there is a player, the player controls a certain set of resources and so on. So then we are going to finally look at another example, if we have time. That's network formation games, and that's related to network design. So that's pretty much that the players need to form a network, so to build connections in order to achieve their goals, and of course they want to play as little as possible. And we're going to prove when we have equilibria, pure equilibria, I mean. Usually, yeah. when we have when we have equilibria, and when we do have them, we're going to analyze the efficiency. So first, the definitions of price of anarchy, stability, and their uses, and then concrete examples. Okay. So we want to know which selfish behavior is socially harmless and there is no needing control, and when we do need some control, and when there is no even use for any control because any stable state is bad. So that's exactly what we looked at in our examples. Admittedly, the examples were of course very simple, but we need to know this in practical cases. And for example, that's important on the internet. It's good when we can say that a social behavior is harmless, in the sense that any equilibrium is good. It's either optimal or close to optimal, because it's not easy to implement some strict regulation on the internet. And as I said, it's not something we want to basically. So definitely it's good when we can prove that any stable state is already promised to be good. So for this goal, we need to define measures of efficiency. And now I'm going to define to explain the rationale behind them. And so we're going to mention to define the price of anarchy and stability, what we have already seen. I'm now going to give you a bit of a broader understanding why that's important and good, and what else can be done, so that you have a higher level understanding. By the way, for the exam, the most important thing that you have is a general understanding. I won't reduce many points for like a technical misstep, but I do want you to understand the basic ideas. So ask me if you don't understand the basic ideas. So the measures we are looking at, pretty much, they look at the optimum social welfare. Optimum social welfare. 1 second. Optimal sounds like it cannot be improved by adding something monotonously, but it can be improved in other ways. But no, I am going to talk about just something which is the best. So the measures are roughly the optimum social welfare and their ratio to the social welfare in a given solution. That's the measures we are going to see, the ratio. When both are zero, so when the solution gives something which is zero and the optimum is zero, we define, it's not defined 0 over 0, but we define it as 1, because we achieve the best possible, even though the best possible is 0. So that's the rationale saying it's 1, because 1 means it's optimum. And the closer to 1 the ratio is, the closer the closer we are to the optimum. The closer the optimum solution and the social welfare the closer the optimum social welfare in any profile, and the social welfare in a solution is R. I remind you that solution can be any group of strategy profiles which we assume are reasonable to expect, are somehow stable. It can be Nash equilibrium, it can be strict Nash equilibrium, it can be a strict dominant strategy profile, it can be something else. Mostly we are going to look at Nash equilibria, but this all can be defined generally. And yeah, I said it can be anything. Our default is Nash equilibria. Now, Nash equilibria can not exist, and if there is no Nash equilibrium, then of course this efficiency concept is not well defined. But if we have multiple solutions, then we need to say which one we consider. So the one with the highest social welfare, the one with the lowest social welfare, something in between. We need to say which one we consider. And the social welfare is also something which can be defined differently. In this course, I'm going to assume by default that it's utilitarian, so that it's simply the sum of the costs. But it can be also defined to be egalitarian, so that we looked at the maximum cost. If you talk about cost, then players want to minimize that. So the worst is the maximum here. And minimizing the maximum cost is caring for the worst player, for the worst of player. If it's about utilities, not about cost, then of course we want to look at the minimum utility. So again, care for the worst of player. That's egalitarian. So we want something equal to everyone. If we use egalitarian, that's what we achieve. But well, that's what we look at. But we are going to use utilitarian social welfare, so which it's the total cost or the total utility, unless we say otherwise. So the default are Nash equilibrium for solution and the ratio between the optimum solution in some social welfare, the optimum social welfare in some profile, and the social welfare in a Nash equilibrium, when the social welfare is defined in the utilitarian way. Now, we are not going to deal with those topics, but they are definitely important to deal with in general. So, first of all, we need to ask whether this solution, for example, in Nash equilibrium, can be reached in practice, and if yes, how quickly. Say there is some best response process which tries to arrive there. Will it arrive? If yes, what can we say about the conversion speed? That's important. It's not always that we can go there, especially not always quickly. Definitely it's not always quickly. In general, it's a hard problem. Now, when fast convergence is not guaranteed, we might want to extend the solutions so that we will be able to converge there, or preferably fast. And when we extend the solution set, then we may need to prove another efficiency bound, because then we have more solutions to pick from. Okay, so that's something which we don't look at in our course, that's out of our scope. And now let us define the social welfare. So given a game, the utilitarian social welfare, which is our default, as I said, is the sum of the utilities. However, if the game is defined with cost instead of utilities, so something we want to minimize, something each agent, we assume they're rational, minimizes, then the social cost is defined as the sum of the costs. So it's very simple here. Now, which solution concept do we look at? Nash equilibria. What if there are several? We can look at the Nash equilibrium with the worst possible social welfare, and that's the most famous solution concept, price of anarchy. Always the best possible. That's also important. That's the price of stability. So the price of anarchy means that the price we may have to pay for simply letting players play however they want for their self-interest. So that's the ratio of the best possible social welfare relatively to the worst possible that can be in an equilibrium. And the price that we have to pay, even if we pick the equilibrium to be the best possible, is the price of stability. That's something we always have to pay. And that's the ratio of the maximum possible social welfare to the best possible social welfare in an equilibrium, when we are constrained to the equilibrium. And if we talk about cost, then the cost in an equilibrium cannot be larger than the best possible. Excuse me, they cannot be smaller. So then, how worse we are relatively to the equilibrium is the ratio of the maximum possible social welfare how worse an equilibrium is not the ratio of the best possible utility to the equilibrium, but is the other way around. We always want price of anarchy and stability to be more than 1. That's the price. How much we lose. So price of anarchy, that's going to be the maximum cost in a Nash equilibrium, which is always at least the cost which is optimum. Typically it will be more. So the maximum cost we may be forced to pay in a Nash equilibrium relative to the minimum cost in any profile. That's the price we may have to pay. That's the worst we may have to pay for letting players do what they want. And we have to pay at least the minimum cost in Nash equilibrium relative to the minimum possible cost, the price of stability. So in both cases, the price of anarchy and stability are at least 1. And the closer they are to 1, the best we are in an equilibrium. So price of anarchy talk about the worst case. The bound will just say what is the best case. So if you can bound that, that's our safety level. And price of stability, the best case, it's relevant when we can influence players to do something, and then we assume that we can kind of prod them to be in some state, so we don't know how to bound any stable state, but we know that if they play what we want, then that can be bounded by the price of stability. So there exists a good stable state. So of course the price of anarchy is the kind of holy grail of what we have, but the price of stability is still important, and it's important, as I said, what we define as social welfare, and here the default is the sum of the utilities of the cost, and which equilibrium from which solution concept we use, because we can invent many solution concepts, and we look at the Nash equilibrium by default. And of course the question can be why should we look at price of stability? Because we cannot, if we bound the price of stability, it does not guarantee us anything, because we don't know that we will play that equilibrium. Yes, but sometimes it's the only bound there is. Moreover, sometimes we can just initiate some equilibrium, like in the network, and then there is a good chance the players will stay there. So it's reasonable to assume that players will play whatever we tell them, as long as it's in equilibrium. So it's reasonable to look at the best equilibrium. And sometimes this can be recommended at the protocol level in many applications. So it's reasonable to study the price of stability, but it's not reasonable there is no need to say what happens if we randomize, because again, it's not like safety bound, it's something we speak about a concrete recommended state, so it's usually not studied for for randomized solution concepts. It's usually studied for non-randomized solution concepts. And another thing which is not in our scope, we look at the best possible Nash equilibrium and the worst possible. What about in between? What about a typical Nash equilibrium? Well, we can assume that there is some distribution about what players want, know, and so on. As you can guess, that's quite complicated, and that's definitely beyond our scope. So let us look at the first important and famous application domain.